resources in an optimum manner in problem of scheduling, product mix and so on. 7. Enable the management to decide when to buy and how much to buy. The techniques of inventory planning enables the management to decide when to buy and how much to buy. 8. They facilitate the process of decision making. Decision theory enables the businessmen to select the best course of action when information is given to probabilistic form. Through decision tree techniques, executives' judgment can systematically be brought into the analysis of the problems. Simulation is another important technique used to imitate an operation or process prior to actual performance. The significance of simulation lies in the fact that it enables in finding out the effect of alternative courses of action in situation involving uncertainty where mathematical formulation is not possible. Even complex groups of variables can be handled through this technique. 9. Through various quantitative techniques, management can know the reactions of the integrated business systems. The integrated production models techniques are used to minimize cost with respect to workforce, production and inventory. This technique is quite complex and is usually used by companies having detailed information concerning their sales and cost statistics over a long period. Besides, various other OR techniques also help in management people taking decisions concerning various problems of business and industry. The techniques are designed to investigate how the integrated business system would react to variations in its component elements and/or external factors. 1.5 Limitations. Quantitative techniques, though, are a great aid to management, but still they cannot be substitute for decision making. The choice of criterion as to what is actually best for the business enterprise is still that of an executive who has to fall back upon his experience and judgment. This is so because of the several limitations of quantitative techniques. Important limitations of these techniques are as given below. I. The inherent limitation concerning mathematical expressions. Quantitative techniques involve the use of mathematical models, equations and similar other mathematical expressions. Assumptions are always incorporated in the derivation of an equation, and such an equation may be correctly used for the solution of the business problems when the underlying assumptions and variables in the model are present in the concerning problem. If this caution is not given due care, then there always remains the possibility of wrong application of the quantitative techniques. Quite often the operations researchers have been accused of having many solutions without being able to find problems that fit. 2. High costs are involved in the use of quantitative techniques. Quantitative techniques usually prove very expensive. Services of specialized persons are invariably called for while using quantitative techniques. Even in big business organizations, we can expect that quantitative techniques will continue to be of limited use simply because they are not in many cases worth their cost. As opposed to this, a typical manager, exercising intuition and judgment, may be able to make a decision very inexpensively. Thus, the use of quantitative techniques is a costlier affair, and this in fact constitutes a big and important limitation of such techniques. 3. Quantitative techniques do not take into consideration the intangible factors, i.e., non-measurable human factors. Quantitative techniques make no allowances for intangible factors such as skill, attitude, vigor of the management people in taking decisions, but in many instances success or failure hinges upon the consideration of such non-measurable intangible factors. There cannot be any magic formula for getting an answer to management problems. Much depends upon proper managerial attitudes and policies. 4. Quantitative techniques are just the tools of analysis and not the complete decision-making process. It should always be kept in mind that quantitative techniques, whatsoever it may be, alone cannot make the final decision. They are just tools and simply suggest best alternatives, but in final analysis many business decisions will involve human element. Thus, quantitative analysis is at best a supplement rather than a substitute for management. Subjective judgment is likely to remain a principal approach to decision making. 1.6 Functions and their applications. Functions. A function is a technical term used to symbolize relationship between variables. When one or more independent variables are related to dependent variables, then the dependent variable is said to be the function of independent variables. A function explains the nature of relationship between dependent and independent variables. A relationship may be a formula or a graph or a mathematical equation. Examples of this type of relationship are price of a commodity and its demand, advertising expenses and sales, income and expenditure, etc. This relationship is denoted by the concept of a function. If a dependent variable y is a function of an independent variable, function is expressed as y equals fx, or y equals fx, and read as y is a function of x. If the value of a set A belongs to x, generate another set B consists of values of y, then the function is expressed as f, a, b, and read as f is a function from A into B, or A maps into B. Here set A is called the domain of the function and set B is called the range of the function. for any arbitrary value a belongs to x, gives a unique value f, a corresponding to y, generally for n independent variables x1, x2, x3, xn, and y as a dependent variable. The function can be given as y equals f, x1, x2, x3, xn. Some examples of functions are given by y equals x15, 0, x, 1, y equals x2 plus 6x2, 1, x, 2, in I. The domain of x is the closed interval, 0, 1, and the range of y is -15, -14. In the 2, the domain of x is the interval 1, 2, and the range of y is 5, 14. 1.7 Construction of functions. Many times in business, we commonly talk about profit functions, loss functions, cost functions and revenue functions, production function, demand and supply function, consumption function, into function, onto function, polynomial function, absolute value function, step function, inverse function, rational and irrational function, algebraic function. The functions are usually set up following the definition and calculation of the functional values. Now we will take some few examples to illustrate the method of constructing such functions. Example 1. A factory has 100 items on hand for shipment to a destination at the cost of Rs1 apiece to meet a certain demand D. In case the demand D overshoots the supply, it is necessary to meet the unsatisfied demand by purchases on the local market at Rs2 apiece. Construct the cost function if x is the number shipped from the factory. Solution: suppose Cx denotes the cost function. If dx, Cx equals x plus 2, dx, if dx, Cx equals x, it can be combined into a single representation by writing Cx equals x plus 2 max, 0, dx. This definition of Cx is seen to be equivalent to the earlier one by considering separately the cases dx and dx. Example 2, if fx equals 2x plus 1, find the range if domain is -1, 2, 3, and hence find the function. Solution: here fx equals 2x plus 1 equals f1 equals -1x2 plus 1 equals -1 equals f2 equals 2x2 plus 1 equals 5 equals f3 equals 3x2 plus 1 equals 7. So, and range equals -1, 5, 7. F equals -1, -1, 2, 5. 3, 7. 1.8 Classification of functions. We have already learnt that for a function f, ob, f associates all elements of set A to set B, and each element of set A is associated to a unique element of a set B. Thus, we may associate different element of set B, or we may associate more than one element of set A to same element of set B, but same element of set A cannot be associated with more than one element of set B. Also, all elements of set B may or may not have their pre-images in A. 1.8. 1 Functions related to economics. In the case of functions in economics, the variables are hypothetical quantities and not actual observable quantities as in physical science. The range and the domain of economics functions are made up of non-negative quantities so that the graphs of these functions are in first quadrant only. In other words, for the purpose of economic analysis, only that part of a curve is relevant which lies in the first quadrant. 1. Demand function. As we know that the quantity demanded of a particular commodity by the buyers in the market is depending on the price. As the prices increases, the demand is decreases, shown as figure. If Q is the quantity of a commodity demanded and P is the price, then the demand function is given by Q equals F. P shows Q depends on P price. P equals G. Q shows P depends on Q. For example, Q equals a BP, or Q equals 10/P, capital P, price, or Q equals 10 page 2 plus P plus 5, demand, capital X, demand function. 2. Supply function. Price of any particular commodity in the market depends on the quantity of supply. As the quantity of supply increases, the prices also increases. If X is the quantity of supply and P is its price, then the supply function is given by X equals F, P, or P equals F, X, capital P, price, supply, capital X, supply function. 3. Cost function. 3.1. Total cost function. 3. 2. Average cost function. 3.1 Total cost function. The total cost, C, which is equal to sum of fixed cost and variable cost, of production in a firm, is depending on the quantity produced of a particular commodity. As the production increases, the total cost also increases. If X is the quantity produced at total cost T, then the total cost function is given by T equals F, X. 3.2 Average cost function. Average cost function or cost per unit is obtained by dividing the total cost function by the quantity produced. Average cost function A equals Tx equals F X X. 4. Total revenue function. The total revenue in a particular commodity of a firm is depending on the number units sold. If P is the price of any commodity and Q is the quantity sold, then the total revenue function is given by R equals PQ. And the average revenue function or revenue per unit is obtained by dividing the total revenue function by the units of quantity sold. It is equal to price, P, of the commodity. AR equals RQ equals PQQ equals P equals price. 5. Profit function. Profit on a particular commodity of a firm is equal to the difference or total revenue and the total cost. The profit function is given by Z equals R, T. 6. Production function. The output product is depending in the various inputs like capital, labor, raw material, etc. If Q is the output quantity of a particular commodity and X, Y and Z are the input variables in a firm, then the production function is sin Y. Q equals F, X, Y, Z. For example, if labor, 1, and capital, K, are inputs variables, then the output is given by Q equals F, L, K, equals Al, Oi, Greek letter alpha plus Greek letter beta equals 1, where A, Greek letter alpha and Greek letter beta are constants, is known as Cobb-Douglas production function. 7. Consumption function. The total consumption function of a firm is depending on the income. As income increases, the consumption expenditure also increases. If C is the consumption and I is the income, then the consumption function given by C equals F, 5, equals A plus B, where A, B are constants. Example 1. A company sells X tins of chicken each day at Rs 80 per tin. The cost of production and selling price of these tins is Rs 50 per tin plus a fixed daily overhead cost of Rs 18,000. Determine the profit function. What is the profit if 2,000 tins are produced and sold a day? Find out the number of tins produced in a day with no profit and no loss. Solution. Per day X tins of chicken are produced with cost Rs 80 per tin. The revenue received per day is revenue function. R, X, equals 80X. The cost of production per day cost function is Cx, equals 1,800 plus 50 times. If P, X, is the profit function is given by P, X, equals Rx, Cx, equals 80 times 50x plus 1,800, equals 30x 1,800. If 2,000 tins are produced and sold in a day, then the profit is given by P, 2,000, equals 30x 2,000 18,000, equals 60,000 18,000 equals Rs 42,000. B for no profit and no loss, then profit function is 0. P, X, equals 0 equals 30x 18,000 equals 0. 30x equals 18,000, X equals 18,030, equals 600. 600 tins per day. 1, 8, 2. Some special functions. In this case, we have some special functions which can be used in economics as well as computer science area 2. These functions are defined as follows. 1. Polynomial function. The general form of the function, f, x, or y equals f, x1, x2, x3, xn, equals an xn plus and 1 xn1 plus and 2 xn2 plus a 0, I, where I is are real numbers, a 1 0, and n is positive integer is called a polynomial of degree n. The real constants n, and 1, and 2, a 0 are called coefficients. The exponent n is called the degree of the polynomial. 4. N equals 1, the equation, can be written as, y equals a 1x plus a 0, a 0. This is usually written as y equals a plus bx, b0, where equals a 0 and b equals a 1. Such polynomial functions are called linear function, i.e. degree 1, and has the domain, x, xr, b. Now for n equals 2, the equation, I, can be written as, y equals a 2x2 plus a 1x1 plus a 0, a 2 0, or, y equals x2 plus bx plus c, a 0, where equals a 2, b equals a 1 and c equals a 0. Such polynomial functions are called second-degree functions or quadratic functions. The x-intercept of a quadratic function is very important. The x-intercept is that point, or points, at which the graph crosses the x-axis, that is, the point at which y equals 0. If such points exist, they satisfy the equation, x2 plus bx plus c equals 0. The graph of the linear function is the straight line y equals a plus bx which cuts the x-axis at a distance b a units from the origin and y-axis at a distance of a units from the origin as shown. Capital Y, capital O. Functions like fx equals x3 plus a0, b, y equals a plus bx, bb 0, inverse mapping, x2, gx, equals 2 plus x, x4, are polynomial function but 2x plus x2/3 is not a polynomial function, capital X. 11 Example 1, the demand for certain item is given by Q equals 153p where Q denotes the amount demanded and P the price per unit. It costs Rs4 to produce each unit. What is the profit function of the firm for this item? Assume Y equals total profit, R equals total revenue, C equals total cost. Since R equals PQ, C equals 4Q, profit equals total revenue total cost, Y equals R, C equals PQ, 4Q equals Q, P4 equals 153p, P4 substituting Q equals 153p, given, equals minus 3 page 2 plus 162p minus 600 which is a quadratic function in page 2. Absolute value function, the functional relationship of the form fx, or y equals dot, x is known as an absolute value function, where x represents the absolute value of x and is defined as given below, and the graph of this function is also shown. 3. Step function, if a function is defined on a closed interval, a, b, and assume a constant value in the interior of each subinterval, say, a, x1, x2, x3, xn, b, of, a, b, where a, x1, x2, xn, b, then such function is called a step function. Symbolically it may be expressed as, y or f, x, equals key for all values of x in the if subinterval. The graph of this function is given below, x, for x equals 0, y equals dot, x equals x, 0, 0, x equals 0, x, y, y3, y2, y1 step function. 4. Convex set and convex function. A set S of points in the two-dimensional plane is said to be convex if for any 2 points, x1, y1, and x2, y2. In the set the line segment joining these points is also in the set. Mathematically, this definition implies, x1, y1, and x2, y2, are 2 different points in S. Then the point whose coordinates given by Greek letter lambda x1 plus 1 Greek letter lambda x2, Greek letter lambda y1 plus 1 Greek letter lambda y2. 0 Greek letter lambda 1 must also be in the set S if Greek letter lambda equals 0, then we get the coordinates, x2, y2, and the given point. But, if Greek letter lambda equals 1/2, the corresponding point on the line segment is, x1 plus x2, 2, y1 plus y2, 2. This point lies in the center of the line segment joining 2 points x1, y1, and x2, y2. The examples of convex set are circle and triangle. The examples are given below for convex and non-convex sets. Convex function, a function fx, defined over a convex set S is said to be convex function if for any 2 distinct points x1 and x2 lying in S for any 0 Greek letter lambda 1, f, Greek letter lambda x1 plus 1 Greek letter lambda, x2, Greek letter lambda f.